Okay, in this video we're going to have a think about what do covalent bonds actually look like. You obviously can't look at them, but try and visualize what they're like. So if we go to methane, we've got our dot cross diagram for methane. Well, let's first of all think about, before we even think about that, let's think about carbon. And we know that we've said that there are 2 electrons in the first shell, and there are 4 electrons in the second shell of carbon. And you've got the nucleus in the middle of the atom. You've got the 2 electrons here whizzing around in orbits, and you've got those 4 electrons whizzing around in orbits. Okay, so that is the model of the atom that we've used since year 8 or 9. Let's have a think about a methane molecule now. And so we've got our, it's like this, 4 hydrogens. See, this is CH4. And we've said we put a dot and a cross, and every overlap, and those pair of electrons are being shared. Well, this obviously doesn't work out. The atoms can't be orbiting all the time and being shared. That's impossible. So it's quite clear that although dot cross diagrams are very useful, and we've always thought of atoms as electrons orbiting the atom, we've got to come up with a slightly better model of what's going on, because this is not really working. Right, so let's think about the simplest covalent molecule that we can possibly have, which is hydrogen. Okay, the H2 molecule. And we've got a pair of electrons in there. Okay, now the new idea of electrons is we don't think of them as little point charges orbiting. We think of them as a negatively charged cloud. Okay, clouds. Right, those clouds are only allowed to take certain shapes. And those shapes are called orbitals. Obviously, the word comes from the word orbit. So electrons are allowed to occupy certain shapes only, and we're going to call these orbitals. And the rule is you're only allowed a maximum of 2 electrons in one orbital. Okay, so I'll rub this out here and I'll show you. This is what we're actually, hydrogen. We think a hydrogen molecule looks something like this, right? We've got a hydrogen nucleus here. There's a hydrogen nucleus and another hydrogen nucleus here. And in between them, we have this bonding orbital, it's called. So we have this orbital, and in there, we've got sort of fuzzy, negatively charged cloud. Okay, so just think, so this is just all a cloud, and it's filled up with negatively charged, and you can fit 2 electrons in there. Okay, so let's think, how does that work in holding to the 2 atoms together? So here we've got this is the hydrogen nucleus, which is positive. And here we've got the hydrogen nucleus, another hydrogen nucleus, which is also positive. And here we've got all this negatively charged electrons. Okay, so there's going to be a force of attraction for this nucleus for the negatively charged electrons, and for this nucleus here also for the negatively charged electrons, and that's going to hold the whole atom together. That's what a covalent bond is. It's the attraction for all this negatively charged cloud between the 2 nuclei. Okay, so that's the simplest covalent bond. Now you may think, like I said here, you've got a maximum of 2 electrons in one orbital. You may think, well, how can you fit 2 electrons in there when they're both negatively charged? Surely they'll repel each other. Well, electrons have this property called spin. Okay. Okay, now they're not really spinning round. It's a quantum mechanical property, but it's analogous to the electron spinning, but it's not the electron spinning. And this can have 2 values. Spin can be either up or it can be down. And for the 2 electrons to occupy the same orbital, they've got to have opposite spins. We'll talk a bit more about electron spins later, but that's how you can fit 2 in the orbital. Okay, so all very well for hydrogen then. Let's try and think about what a more complicated molecule like methane might look like. Okay, so let's think about methane. Okay, and we've got the dot cross diagram. We're going to have the electrons like this. Now methane actually has, so you have your carbon atom in the middle, and you're going to have 4 orbitals. Okay, so I'm going to draw one here, this sort of shape, and then you have another one, another one. They're all supposed to be the same size, and if you can visualize this as 3D, well, here's the hydrogen nuclei. Yeah? The hydrogens would form the edges of a regular tetrahedron. Okay, so you'd have sometimes people draw it like this. So you have your carbon there. You've got this is one of your orbitals sticking up here to the hydrogen. You've got another one. This is in the plane of the paper, and this one I'm going to draw like that. That means it's coming out towards you. Okay, and the last one is dotted line. That means it's going back away from you. And so all those hydrogens would form the edges of a regular tetrahedron, regular 4-sided figure. So that's so you can visualize it. So you've got your carbon there. There's your carbon nucleus. And these are your hydrogen nuclei here. Okay, each of these are called bonding orbitals. You've got 4 of them. Each bonding orbital has got 2 electrons in it. And one of those electrons comes from the carbon, one comes from the hydrogen, and they've got opposite spins. What's holding the whole thing together, like in the hydrogen? Well, this is all negatively charged here, isn't it? Yeah. And the carbon nucleus is positive, the hydrogen nucleus is positive, and so they're both attracted together. Incidentally, these orbitals, they try and get as far away from each other as possible, because they're negatively charged and they don't like each other, they're going to repel, and that's why it forms this regular tetrahedron shape to get as far away as possible. So just quite often, if you draw, when you're doing organic chemistry in year 11, you draw methane like this, wouldn't you? You draw it as like that, and that's not really what it, because that makes it look like it's 90-degree bond angles here, doesn't it? Okay, but it's not 90-degree bond angles. It's because we're drawing something which is 3-dimensional on a flat piece of paper. That's why we have to draw it like that. But it doesn't really. That's not the shape. If you just have a think about these bond angles here, these are actually quite a bit bigger than 90 degrees. These all manage to be about 109 degrees. Okay, in a regular tetrahedron, that's what they are, and they're getting further away from each other than they would do if they were just all flat like that. So the methane molecule is not like that at all. Okay, so each of those pairs of electrons, yeah, we can see here, they are in these bonding orbitals. Okay, now let's have a think about what ammonia would look like, NH3, because that's got some electrons in the outer shell which are not involved in bonding. So we'll have a look at that now. So let's have a look at ammonia. Right, so we have nitrogen there. A dot and a cross in each of those. We've only drawn 3 electrons from nitrogen there. Nitrogen, of course, is in group 5, so we need to draw a pair of electrons there to make 5 nitrogen electrons, so a total of 8 in the outer shell. And so what that looks like is quite similar to the methane. So if I had the methane, I'd draw the methane like this. But what happens is, so in this is the nitrogen nucleus here. So you've got a pair of electrons in each of these orbitals, okay? These are called bonding orbitals. There's 3 of them there. There's a hydrogen nuclei. But this top one is a different shape, so I'm going to get rid of that. I'm going to rub that out. It isn't that shape. It's more like this. Okay, it's more bulbous, and this is usually called. There's a pair of electrons, and then they call it a lone pair of electrons. Okay, so that orbital's got a different shape, and the reason why it's more squashed is because if you think it's only got, this is all negatively charged electrons in here, isn't it? It's being attracted towards the nitrogen nucleus here, but there's nothing here where I've just drawn in green. There's nothing there. There's no positive charge to attract it that way, so that's why it's held closer to the nitrogen. So it's a different shape. So that's what an NH3 molecule would look like. Let's see what water would look like. The next one. So H2O. Well, if I remember from the previous lessons, we'd have a pair of electrons there. Oxygen is in group 6. There's only 2 crosses for oxygen there, so it should have 6. So I need to draw 4 more. So 2 electrons there and 2 there. Now you can see that the the water molecule is going to have the ammonia one that had 3 bonding pairs, and it had 1 lone pair. Whereas you can see water is going to have 2 bonding pairs and 2 lone pairs. Right, so 1 minute. Okay, so there's a hydrogen nuclei there, and there is the oxygen, and then it's going to have 2 lone pairs. So it's going to be that sort of shape. And you probably recall whenever your teacher was drawing water molecules, they would probably always draw water like that. Okay, they always draw it like that. They don't draw it as a straight line, because the reason why water isn't a straight line, it's bent like that. And the shapes of these molecules has an important effect on the way they react sometimes. So, and we'll we'll move on to that later. So hopefully this has given you some idea of how molecules, how they'd actually look, how the electrons look, and get away from this idea of electrons being just orbiting, like point charges orbiting the nuclei. It's much more useful to think of occupying these things which are called orbitals, which are negatively charged. Well, they're clouds, but they're only allowed to occupy certain shapes. You fit 2 electrons in each orbital. So more about that later.